Thanks, everyone. So first, I would like to thank Dieuleveut several times for guiding me through the campus, indicating me all the mistakes I could make with the metro, having me around. This was something we planned more than a year ago, and we had plans to do it online. And I happened to be on the East Coast this week, so I was so happy to give the talk on site. I'm going to talk about joint work with Baptiste Gougeot, who graduated of his PhD last spring, and is going to be an assistant professor in Télécom Sud Paris, which is another school of our institute. So the way France works is that we have plenty of small schools that date back. Try to make mergers, then the mergers fought, so they got divorced, and now you have a new merger, and the new merger you should remember about is this IP Paris, which stands for Institut Polytechnique de Paris, and which is composed of École Polytechnique and 6 other schools. So I should have put the logo as a huge font, but maybe I can even try that. So it's École Polytechnique. Oh, it's never going to work. École Polytechnique is one of the 6 schools that constitute IP Paris. And we also have an AI institute for those that are into AI or data science, which is with that institute and HEC, a business school. So we try to be as interdisciplinary as we can. And this is going to be something we advertise a lot because we just got a big funding of 70 million, which at the scale of France is huge for us. So we're really trying to do our best, especially through collaborations in the institutes.
And
so,
is that also part of this 6 co-located with this?
Yeah, this is co-located. So in some sense, this just encompasses HEC and that. HEC is, 20 minutes away by bus. It's the same place. Okay, so I'm going to talk about heavy ball. And although Dieuleveut gave you hints, I'm not going to say what the result is for the moment. But I'm trying to understand how fast heavy ball method can be and the limits of that method. And okay, this is the short version of the talk. That goes straight to the results, is about 15 minutes, 20 minutes, but doesn't provide much insight on why we knew those techniques would work. So I'm going to give you the detailed version that does a few detours and covers a few things that I think are nicely related. So, okay, the roadmap, and oops, the roadmap is that. I need that to be just exactly full screen. Okay, the roadmap is the following one. I'm going to talk a little bit about things that already we knew for more than 50 years on heavy ball method, and not because this is it's not only out of curiosity. This is really because I believe that understanding properly how the rate behaves is other methods. This goes far beyond heavy ball. This could apply to many other methods you want to look at, and how this connects to performance estimation. So I'm going to do a short crash course in one slide on performance estimation, making sure that everyone needs the basics. And then we finally get to answer the main and principal questions is, can heavy ball method accelerate on the class of smooth and strongly convex functions? Okay, so where do we start from? We start with a slide that has 2 definitions. I really wanted to fit these definitions somewhere else as we made progress in the slides. I couldn't, so slide number 1 is just 2 very basic and very simple definitions. What is the class Q mu L that I'm going to use a lot? I'm going to try to use the pointer because people online can see what I point to. So class Q mu L is the class of quadratic functions that are typically parameterized by Hessian matrix H. And so, I mean, FH minus F star is just X minus X star. Is H X minus X star. And then the class of smooth and strongly convex quadratic functions is those for which the Hessian matrix has its eigenspectrum between mu and L. Very easy. And more generally, the class of smooth and strongly convex functions are the functions for which, when the easiest way to define those is, say, we assume that Y is differentiable. We assume that Y is differentiable, and the Hessian matrix has to have its eigenvalues between mu and L at any point. Okay? It's clear that like 2 of the most classical functional classes in optimization. The reason why those functions make sense, we could actually connect that to performance estimation. These are the classes that most people have tried to derive rates. Okay, so now we're going to talk about algorithm, and especially the most basic one is gradient descent. I'm not even sure that Cauchy 1847 is the first instance of gradient descent, but gradient descent basically, one of the issues that we have with that is that it poorly behaves for poorly conditioned functions. So here I have represented a very simple quadratic function again, two-dimensional one, and my gradient is orthogonal to the level set at any point, and because of that, basically I make very little progress. So I'm going to suffer strongly from the poor conditioning of the function, which is here my function is very steep in the horizontal direction and very flat in the vertical direction. Okay, and so how do we solve that? At least partially, heavy ball, which is also known as Polyak momentum, is one of the famous methods that has been introduced in order to make progress with respect to that dependency on the conditioning. So the way the heavy ball method works is that we have now the same as gradient descent. Again, I'm going to try to force myself to use that. So the same as gradient descent plus a momentum term now that is a beta momentum coefficient times xt minus 1. So what I'm doing when doing that is that I'm accumulating the progress in the direction in which I have been moving consistently. So if I look at the graph now, instead of moving here, I'm going to move here plus add up the previous step, which makes me move much faster towards the optimal. And this shows in the rates. So that are the rates that are the most very classical. So it all depends on the conditioning number, kappa, which is mu over L. So I use kappa smaller with respect to 1. Both conventions exist. We can take just the inverse. And the rate for gradient descent is basically depending on the 1 minus kappa to the t. It's all a linear rate because those methods are deterministic and we are smooth and strongly convex. So we have a contraction at each step that basically scales with 1 minus 2 times kappa, as kappa is small. Right? So that's the important part for gradient descent. And for heavy ball, we actually have something that scales with square root of kappa. I'm going to show you which parameters of gamma and beta we need to obtain. Okay, so heavy ball is, for theoreticians like me that do theory of optimization, the best success story ever. I mean, we didn't invent it, right? It's invented by Polyak in '64. But the good thing is that the way it was designed was purely theoretical at the beginning. So Polyak looked at the best possible method that you could do, which was Chebyshev polynomials. And Chebyshev polynomials actually are meant to optimize the distance towards the optimal point at any step. But Chebyshev polynomials is a second order system, as basically any family of orthogonal polynomials is a second order system. And if you look at the second order system, you get basically some kind of Polyak momentum steps with varying gamma and beta. And if you look at the limit of those gamma and beta, you get the optimal tuning for that fixed step size. And that fixed step size things achieves that rate 1 minus 2 square root kappa to 20. Yes, you have a question.
But acceleration only holds in asymptotic sense, right?
Okay, so that's an excellent question. What do I mean here by asymptotic, right? So actually, we could have something which is non-asymptotic. Okay, so the reason why we have this asymptotic is because we're going to have a matrix which is non-symmetric. I'm going to give several details on that. And so typically, we would have some factor t here in front of that if we wanted to have something really non-asymptotic. That's why I've used this sim x sign. But actually, I think we really care about the asymptotic question. Oh, okay, I'm done. That's an excellent question. It's true that the rates are asymptotic. I don't think it matters too much. And that makes the story on quadratics simpler to go through. So I'm only going to talk about asymptotic rates in some sense, but anything that I say asymptotic can be made non-asymptotic, paying at most some polynomial factor. Great, so it's really that the good story is we invented, Polyak looked at something super theoretical, Chebyshev polynomial, and invented an algorithm that is used everywhere today in Perl. So if you do Adam algorithm, there is momentum in that. Basically all the famous to answer is that the rate for gradient descent is the same for smooth and strongly convex functions and smooth and strongly convex quadratics, while the rate for heavy ball is only for quadratics. And I want immediately to, spoil everything by saying that this is not necessarily a question that's going to change the face of the world in the sense that we know another algorithm, which is Nesterov accelerated gradient descent, that basically puts the momentum step first and then takes the gradient step. And that algorithm does achieve acceleration on the class IEOR. Okay, so the reason why we're interested in understanding is that still most people use heavy ball momentum. And even from a safety perspective, you could say, what we're going to show, I'm spoiling it already, is that heavy ball is not going to accelerate. And we could manually construct adversarial functions. For example, a logistic empirical risk that would make heavy ball fail. So and we're going to see how we do it. Okay, so how do we obtain those rates? Let me just find a place where I have time available. I will ask you once in a while. Okay, so how do we get those rates? The analysis is the best. I mean, for those who have a lecture to teach on optimization, those are the best exercise ever to give, right? Gradient descent. For quadratic functions, you basically write that as a linear system. Once you have that as a linear system, this is a symmetric matrix. At each step, you contract by something, which is the spectral radius of that matrix. How do you do it for heavy ball? You do exactly the same for quadratic function fh. You can write that as a second order linear system. Now you involve two consecutive iterates, and the matrix A is automatic to obtain when you use that fh is just h times x minus x star. And so you obtain that matrix. And now this matrix is not symmetric anymore. So everything we're going to talk about is asymptotic rates, but we again are going to have a look at the spectral radius of that matrix. And okay, that matrix I cannot directly diagonalize. Again, it's not symmetric, but I can decompose it into d blocks of size 2, and each block of size 2 is exactly that. So what I've written now here, like 1 plus beta minus gamma lambda I, with lambda I being the ith eigenvalue of the matrix H. And I'm only looking now at those small matrices, and I'm going to try to find the worst case spectral radius of those matrices for any eigenvalue that would be between mu. Right? And the answer is here. The answer is that this is actually the color map of the rates. That rate that depends on gamma and beta. So gamma is on the x-axis, beta is on the y-axis, and for any mu and L here, mu over L is 1 over 10. Okay, so you typically obtain something like that, and this is a graph we're going to look at a lot. So I'm going to decompose that graph and explain how we get that graph exactly. So how do we get? I mean, basically, it's the same formula exactly as before. I have my rate that depends on gamma, beta, mu, and L, which is that maximum. And the first question we're going to wonder is this even smaller than 1? And there is a condition for that to be smaller than 1, which is that gamma L has to be smaller than 2 times 1 plus beta. So that creates that shape, which is looks like a trapezoid shape. And I'm going to discuss that, in fact, this is actually a triangle if you push it up to beta equals -1, but I will say a word about that afterwards. And in that area, so within that triangle here, the trapezoid, we have a rate which is smaller than 1, outside larger than 1, so no convergence. Now, that's going to be 3 areas depending on whether those eigenvalues are complex. So they are going to be complex conjugates or real values. And already I can ask you what the best case scenario is, because the determinant of that matrix is always going to be beta. We want the spectral radius to be as small as possible. So either have 2 real eigenvalues for which the product is beta, but one is larger than square root beta, another one is smaller than square root beta, or have 2 complex conjugates, both with modulus square root beta. So we already feel that the best case scenario is when the 2 eigenvalues are complex conjugates. And this is exactly what's going to happen in that first area number 1, which is called the robust region. In that area, for any lambda in mu L, so for any gamma and beta, for which the value falls here, for any mu L, lambda in mu L, the 2 eigenvalues are complex conjugates. And so the spectral radius is always square root of beta. And the good news is that it does not depend on gamma. This is what we call that the robust region. If I mistune gamma, I mean, there's no mistuning of gamma. Any value of gamma on one of those lines. So each of the lines here corresponds to a level set of the rate. So the rate, for example, is constant on all that black line or constant on all that purple line. Does not depend on gamma. Okay? And the rate is exactly square root beta. Then we have the lazy region. In the lazy region, that's the region in which the step size is too small in some sense. So then, in order to improve, you need to actually push the step size to the right. And the more to the right you go, the better the rate. And finally, we have what's called a knife edge, just because it's very small. And in that case, typically, we have the oscillatory behaviors because gamma is very close to 2 over L. And in that case, you need to reduce the step size. And the amazing thing is that the level sets, so the set of tunings for which I get the constant rates form triangles. They're all straight lines. The easy part was to see that it's a straight line in the robust region because it's exactly equal to square root beta and not depending on gamma. the fact that it's a triangle in the other two regions, you actually need to do the derivation. And okay, so now I can put back the color map. We get that the optimal point is going to be, okay, so first I can say that the limit between the knife edge region area and the lazy region is that 2 over L plus mu times 1 plus beta. Not very easy to read, but you recover here the optimal rate for beta equals 0, which is 2 over L plus mu. And finally, we get the optimal tuning for quadratic, which is something that doesn't matter in the following. And the optimal tuning gives you that the optimal beta, basically you want to take the minimal beta while remaining in the robust region, because the smaller beta, the better the rate. So you want to push the beta down to that point, and you get that beta optimal is 1 minus square root kappa divided 1 plus square root kappa, exactly such that the square root of that is the rate I had announced at the very beginning. Okay, so this is an amazing exercise for students. It's a good way to test the ability to do linear algebra, a bit of computation, and still understand things on learning algebra. Now, the rates are given here. They are meant to be small enough so that you can't read them if you want the exact thing. You can look at the paper, right? It's meant so that no one can try to read it. Okay, so summary on heavy ball for quadratics. We know everything. It's the optimal algorithm. It comes from theoretical analysis. The optimal tuning is known. The level sets are triangles, so it's not very easy to see here because the coloring is not perfect, but you can see it's always triangles. And for that single plot, I have added beta up to -1 to show you that it's actually all triangles. And even the trapezoid we are looking at is just because we are always constraining the momentum to be bigger than 0. But it's actually always and has always been a triangle in the algebra, which is hidden below. And the robust region shrinks as kappa goes to 0. So if my conditioning degrades, my area moves, and my optimal beta goes to beta equals 1. So now what do we know about that algorithm on smooth and strongly convex functions? We know 2 things. Some positive results, especially a paper by Taylor, Vanskoy, and Lessard, that showed that there exist parameters, typically parameters which are around here, for which we do have convergence, but not any proved acceleration. And on the other hand, they have negative results. And the negative result, which is the most famous, you said that for the optimal tuning, so for the gamma star, beta star, they, at least I think in this paper by Lessard and Recht, which is and Paccard, it's a very famous paper. In that paper, I think they give it for kappa equals 25 or 1 over 25. For the optimal gamma and beta, they show that we can have a cycle of length 3, meaning that the algorithm is going to loop forever between that point, and that point. And the way they build that is a function which is quadratic by parts in order to have such a cycle. Right? And this paper is sometimes referred to in lectures as showing that there is no acceleration beyond quadratics. It's actually does not show that, because it's not because for the exact optimal point here, I do not have an acceleration, that I cannot just slightly deviate from that point and have an acceleration. And actually, we're going to see at the end of the day, the region why everything is going to happen in order to know if we have acceleration is going to be in the top left corner. Okay, so the fight we had to make in order to prove the result was really to understand what happened here, not what happens. Any questions on that? So now we're motivated to know if we can have cycles. And the second part is about finding those cycles. And again, this part, I could have skipped it, but I want you to understand where we came from. The first paper we had on that was purely numerical. And it showed, we knew we could solve it almost immediately. So why cycles? Again, a small digression. Proving that an algorithm does not behave well is not easy. It's not because you don't get a contraction after 1 step that you won't get a contraction after 2 steps. Maybe you are not looking at the correct metric. Maybe you're looking at the iterated distance while you should be looking at the gradient norm. All those things make it very tricky. If you can prove that an algorithm cycles, meaning goes from x0, x1 back to x0, x1, you know that no metric, no number of iterations that you look at is going to solve your problem. So cycles are really a powerful way to demonstrate failures of algorithms. They can be observed after a finite number of iterations, and if I have a cycle, I have no kind of worst case guarantee. I want to insist again, I'm not showing that for any function within the class, any initialization, I'm going to cycle. I'm going to say that for at least one function and one initialization, I'm going to fail, which is always the case in what we do in optimization. Right? I mean, when we give a rate, it's a rate which is uniformly valid and not, it can be better on specific good functions. And the good news is that finding if there is a cycle, this is an optimization problem. So I'm saying that casting we can cast the existence of a cycle as an optimization point. So how do we do that? We're saying that basically finding a cycle is the same as finding how close xk can be from x0. So after k steps, how close can I be from the initial point for any function within the class, any iterates that corresponds to the result of the algorithm, any dimension underlying. And I have to assume that at the beginning, at least, I move a little bit. If I don't move at the beginning, I could just be always at x star. And the fact that x star is stable is kind of a good property of the algorithm. It's not a failure. So obviously, if I start at x star, I should stay at x star forever. It's not a valid cycle that I'm worried about. Right? So I have to assume that I'm moving, which is what that condition holds for.
Good question.
Yes.
K an optimization parameter or K is given?
K is given. We're going to have to proceed and enumerate all possible nets. Excellent question. Here I've added another parameter, which is L, which is the order of the algorithm. L is, for example, for heavy ball, order 2. And I'm claiming that I have a cycle if this is 0, so if that minimum is 0, meaning that xk fallbacks onto x0. This is a little bit, tiny little bit wrong. I actually need that. I have 2 iterates if I'm an order 2 algorithm that fall back to the 2 first values, right? So I actually need to have that for L consecutive iterates with L the order of the algorithm. Otherwise, I can imagine that I'm coming back, but I'm not repeating exactly this trajectory.
So how do you differentiate between the algorithm not converging versus having cycles? I'm missing something here.
Well, cycles is a very specific case of non-convergence. It really says that I'm going to have a finite number of values, k here, over which I'm going to do x0, x1, x2, and xk is going to be x0, xk plus 1 is going to be x1, exactly the same trajectory.
And how do you impose that xk is going to be x0 here?
Okay, I'm saying that I have a cycle if this is 0, if the minimum is exactly 0.
Got it. I'm the other.
Very good point. Is it a minimum one? If we fought for that, it's actually a min. And the way I'm going to shape things afterwards is talking about actually the feasibility of that being 0. Yes.
We have a situation where we have cycle like but after x0,
Okay, so yes, but then you would remove the first iterate, right?
Not captured.
Okay, but the program is worst case over any trajectory. So I mean, if you would happen to cycle, let's say there's a burn-in period and then you cycle, then you just drop that burn-in and say you start at that. I'm assuming that the algorithm is always stationary in the sense that, I mean, the way it behaves doesn't change over time. Otherwise, I mean, that's really the basic necessity for the argument that I'm going to cycle forever. Okay, and so now I'm going to claim that this is something we knew immediately when we wrote that down. We could solve that. And we knew that because of performance estimation. That's what I'm going to explain in the next slide, this crash course on performance estimation. But before doing that, I'm still going to show you what we get for my trapezoid of values. So we get that in all that area, we get cycles of length 3. This one, cycles of length 4, 5, 6, etc., up to length 25 here. And to draw that plot, we're going to use the SDP relaxation I'm going to talk about in a minute. So because of the SDP relaxation is not very precise, we couldn't really go beyond 25. I'm going to detail that matters now.
Might be a stupid question. So in practice, when we add the momentum, right?
Yeah.
We know that it yields the accelerated rate, but we always perform the averaging to stabilize the average, right? So even you have the cycle for the actual iterates.
So that's a very good question. Do we perform the averaging? It depends. Typically, to obtain the acceleration, you cannot perform. I mean, so in the traditional sense, in the way, for example, Polyak phrased it, or in deterministic cases, you typically don't necessarily use the averaging, because if you use the averaging, then you keep too much of the initial points.
But do local average. Maybe.
Or you could do some kind of tail averaging.
Yeah.
Okay, so that's a good question. The answer I would give to that is that if I cycle, then any tail averaging is going to converge to a point which is depends only on the cycle, and I could mess things up. I could still place the optimal point a bit away from the cycle, the average of the cycle trajectory. I will have to fight a little bit for that, but it's not impossible to do. It's actually a good remark. Okay, so what is performance estimation? Again, who is familiar with performance estimation? Very familiar. So for whom is that obvious that this is easy to solve numerically as an SDP? Okay, I'm still gonna go through the steps because, okay, so basically what we do in performance estimation is the following. It's a very simple case. I've used gradient descent because it's the canonical example. None of that work on performance estimation is mine. We contributed to a package, but it all dates back to the work of Joël Rory and Adrien Taylor and François Gliner, Julien Hendrix, etc. So credits where credits are due. So the one thing we're looking at is, let's say we want for all functions that are smooth and spring convex that after one step of gradient descent, I have that x1 minus x star squared is closer, well, is smaller than x0 times minus x star squared times the coefficient. I want to find the best coefficient here. And I'm saying that finding that best coefficient here is the same as saying that this coefficient 1 minus kappa is the worst case value of the ratio for any function, any x0, any x1, any x star, such that my function is within my class, my x1 is obtained from a gradient descent step, and x star is the argument. Right? And now I'm going to say I can just introduce a slack variable, and that slack variable is G0, which now is in RD, and which is the gradient of f at x0. Right? What I'm trying to get away from is that this problem is non-convex, infinite dimensional, because I'm optimizing over all functions. But I don't care about all functions. If two functions have the same gradient at G0, then they create the same dynamic over one step. So that's why I'm introducing that slack variable G0, and all the rest is the same. Now I can add the fact that x star is assumed to be 0. It's just a translation invariance. So that gives me that I remove the x star, and I can add that x0 star x0 squared is 1. This time it's a homogeneity argument. And you need to work a little bit for that, but you actually don't need to have when the ratio can be transformed into a constraint on x0. And there we are, we'll have that problem, but now we still have an optimization, which is officially over a worst case function f and G0 being the gradient. And now I'm going to say I don't care about what the function f. I'm going to say I'm going to take the worst case over the gradient such that there exists a function. So I'm saying now the question is, does there exist a function in my class such that the optimal point for the function is x star, the gradient at G0 at x0 is G0, and that's it. And this is what we call interpolation conditions, right? The question that does there exist a function that passes through some points? When we talk about interpolation in like, for example, deep learning, the question is whether I can pass through all the points. And that question has a simple answer. So for example, if I say I want to find, I'm looking only at convex function, does there exist a convex function such that for any I, my function value at xi is fi, my gradient at xi is gi? This is true if and only if I have that very simple inequality that you recognize as the basic inequality that I'm above the tangents. And obviously, if I have a function which is convex such that I do have that, but the reciprocates proposition holds true. And it's kind of easy to see that. Let's say for the moment I have like 3 points, x1, x0, x2, 3 values. If I give you 3 gradients like that, so the way I give the gradients is by giving the tangents. Yeah, I mean, obviously you can build a convex function that passes through those points. Just like do the maximum of these 3 functions, and the maximum of these 3 functions is going to interpolate. Now, if I change this gradient here in order not to satisfy one of these inequality, obviously I'm failing because the tangent here would pass above that point. So the gradient is wrong. If I put that value here too low, obviously I'm going to failing because now that tangent passes above that line. Okay, so long story short, knowing the condition on the gradients, the points, and the value for which there exists a function within the class that is both temporary those points is not too difficult. This is the case for convex functions, and this is the case for smooth and slowly convex functions. So this is again a sampled version of what's called the coercivity inequality. And to prove this one, you need a little bit of work. You actually need to go through functional conjugates and finding what the functional conjugate interpolates if the function interpolates on it. Not too difficult. Also an excellent exercise for an exam in optimization.
Yeah, for your course.
Yeah. Okay, and so here now, the amazing news is that I can just remove that existence constraint by a condition on my gradients and function values and iterates, right? And the next good news is that actually I can now observe that everything in that problem is just quadratic in terms of x0, g0, and so I can introduce the gram matrix of the iterates and gradients, and everything is linear. So now I'm saying that this is the supremum for any positive matrix, any gram matrix of iterates, for any positive matrix, there exist points for which it's a gram matrix and reversely. And so I'm looking at the worst case value of G22, the X1's coefficient, for the constraint that G11 on X0 is 1. The algorithmic constraint that equals that is just doing the difference and squaring the norm. This is linear. This is linear. It's all linear in terms of the gram matrix. And so we have obtained an SDP. And so this goes beyond that. I mean, so basically, for any functional class, any algorithm, any worst case guarantee that you would look at for which the performance metric and the initial condition can be written as something quadratic in terms of the gram matrix, I can write the worst case as the maximum of that ratio. It's non-convex, infinite dimensional, but if I go through the sampling, interpolation, homogeneity, and SDP lifting, I get back an SDP. And the important link is that G corresponds to the gram matrix of the iterates and their gradients.
What happened to the rank 1 condition?
Rank 1 condition. Where was the rank 1 condition?
Shouldn't that be a rank 1? G?
There should be like a rank D.
G?
Yeah, there's a rank D condition. If you
No, meaning that this G isn't that rank 1?
no, it's rank D. We
rank
did the
D.
dimensionality. So it's an excellent remark. That's an excellent point. We have hidden here that we're taking the worst case over any possible dimensions. So if I had constrained on the dimensionality of the system, the dimension over which I optimize, then I would get a rank D constraint here. But because I have no constraint on rank, I have no constraint on the dimension, I have no constraint on the rank. But this is actually a very good catch. Okay, and so for those who want to play with that, learn about that, there have been a couple of packages, one by Adrien, Taylor, Julien Dries, François Griner on MATLAB, and afterwards Baptiste with Coates and I, so Baptiste Gougeot still, who was the main workforce on those projects, has a PEPIT package that has more than 75 examples already pre-coded of algorithms that you could look at. So triple momentum, SVRG, I don't know, do your best. And we are looking for people to contribute in that. So whenever you have a review paper of a deterministic algorithm or even stochastic, just implement it and compare what the authors provide as a rate to what is the best possible rate they could have achieved. And okay, so many good things about that. You can actually learn things on the proofs. If you look at the dual of the SDP, you learn things on the proof structure. It's really, for me, one of the nicest line of work in this area. And basically, any performance metric can work. So let's say the maximum of f of xt minus f star can work, the maximum of xt minus x star squared, but also the minimum of xk minus x0 squared. Because at the end of the day, the one thing I required was that it would be linear in terms of the gram matrix. So whether I do maximum or minimum, it's just a linear function. So finding the cycle over the shape I had given at the beginning as the optimization point, when we wrote it down, we knew that we could solve it with PEPIT, and we obtained that graph. What's that?
Like maybe 15 minutes.
15 minutes, that's perfect. So now I can go back to the main story. I wanted really to highlight that part of performance estimation because I think for me this is one of the most important tools. I'm actually struggling to have that in my master's lectures because I believe it's too important for the students to miss that. But it's I'm struggling in the sense that they have so much to learn before they understand that. But still, I think it's a very nice tool to provide. So now what we want to do is have something systematic on all points over which we have a cycle. And we're going to use all this approach. So I just want to be more systematic. And the one thing I'm going to change a little bit is now do the same approach, but as a feasibility problem. So I'm going to try to say for any values of my iterates, I'm going to look at the gradients that I will need to obtain those values as a cycling behavior. And then I'm going to use interpolation conditions to say, are those values possible? Right? So the way it works is say, okay, now for any values that I could look at, so that those values are over which I would cycle, there exists a function for which heavy ball cycles on those iterates. What's the condition? So the first part is just looking at the last part. So heavy ball cycles on those iterates for a function f, if and only if the gradient of the function satisfies this inequality. So at any step, I mean, I just need that when I do my heavy ball update, I get the next step that I wanted to get, which is equivalent to saying that my gradients at point xt has that particular expression. And I have that heavy ball for function f cycles on those iterates if and only if that. And now I have that there exists a function such that this is true if and only if I have the interpolation conditions with those values for the gradients. So this is the conditions that I need and suffice to satisfy to get that f within FML exists. And so now I can just plug two things together. So I want to see if there exists point xi and value fi such that I have my interpolation conditions for any pair ij, with my gradient gi being determined as above, my gradient gj being determined below. And I just plug those values in. And again, I have my SDP reformulation. So the exists, now I can move towards existence of a cycle. NAE is for not all equal. The not all equal constraint is encompassed in the fact that G is different from 0. And we can actually force another constraint on G to ensure that they're actually not all equal. There exists a function f in FML such that a cycle, if and only if there exists a vector f of function values, a matrix G, which is the gram matrix, which is positive, such that FEI minus EJ, it's just FI minus GJ, is larger than that. Right, so now I have my SDP, and again, I can solve numerically, no worries. But that's where things get a bit interesting, because what I really want to understand is what the shape of the cycles are. And that's why I'm going to use something really nice. I'm going to say that, okay, G is the gram matrix of iterates, and I can go back and forth. If I find a matrix G that solves the problems, it means we can go back in the proof. It means that there existed iterates with that gram matrix over which I will have cycles. And so what I'm going to say is that when I look at my SDP reformulation, okay, just exactly as before, I can actually say that if I have a cycle x0, xk minus 1, then x1, xk minus 1, x0 is also a cycle. But now in terms of gram matrix, this corresponds to permuting the rows and columns. And obviously, I could do that again and again. If I have a tree cycle, I can permute it 2 times, and I would permute the rows and the columns each time. But the good stuff is that on the space of G matrices, it's a convex set, or it's a convex feasibility set, the convex problem. So I can actually average out those solutions. So I'm saying now that if I have any solution G, the matrix that I obtain by permuting the rows and columns, because any permutation of the rows and columns is still clearly a cycle, and because it's convex in SDP form, is still a cycle. So now I'm saying that if there exists a cycle, there exists a cycle for which the gram matrix is very simple. Okay, so yes.
But you don't know when you start the cycle, right? Here you assume that you start at x0.
Yes, okay, so we always, I mean, in some sense, when I say cycling of x0 to xk minus 1, it means that my trajectory is going to be x0, xk minus 1 forever. I discount, I mean, anything that would come before, I can ignore because that just corresponds to a specific initialization. Okay, so here with great colors that are meant to show you, even though it's small to read, what a circulant matrix is. A circulant matrix is just a matrix for which the diagonal is constant, above the diagonal and lower coefficient is constant, etc., etc. So it works with slides, right? And this is exactly the shape of matrix that we obtain when we average out matrices that have row and column-wise permuted, right? I can only do circular permutations. That's why I don't get a constant matrix. And so that's my new statement. I'm saying that I have a cycle, which is my PK feasibility problem, if only I have a cycle in SDP form with G assumed to be circulant. And for example, the cycle by Lessard and Resch that I talked about in the beginning, it has a very nice value, right? It's what's taken from the paper by Lessard. And I don't remember those values. But if I compute the gram matrix is rank 1 because those values are in dimension 1 and still ugly. Now, if I do the circulation trick, meaning that I permute an average, what I'm going to get is that actually this is the gram matrix of 1j and j squared, the third roots of unity. So that cycle in dimension 1 is actually the fact that there exists a cycle for the optimal tuning in dimension 1 says that actually for the optimal tuning, there exists a cycle on points 1j and j squared. And we see now where we are going with that. I'm going to say, actually, any circulant matrix I can write as a combination of identity j squared, with j being that matrix. And now I know everything about those matrices. Those matrices to the k right? Here, the dimension is the all of the cycle. G, K to the K is identity. So its eigenvalues are the roots of unity. And it's basically its eigenvectors and its eigenvectors are also vectors composed by the exponents of roots of unity. And I can actually get the spectrum of G as the Fourier transform of the coefficients, discrete Fourier transform C0, Ck minus 1. And actually, I get that any matrix G that is circulant is decomposed as the sum of its eigenvalues times HL, with HL being the Gram matrix of one of those vectors that has one exponential I2pk divided by 10, by n, etc. And so basically, it's the Gram matrix of 2D vectors that represents the roots of unity in full generality. Okay, and so this part is, I would say, the most technical one, but we get two things from that. We get that actually G can be written as only depending on K coefficients with as eigenvalues, all assumed to be positive. So I can rephrase everything as an LP. And that LP, now we can solve much more efficiently numerically. And whenever we have something numerical in the paper, we solve the LP. And second consequence, we have a generic.
Right, just a quick question.
Yes.
How do you conclude that nu-Ls have to be greater than or equal to 0?
Oh, because the matrix is symmetric and positive. And the nu-L are the eigenvalues of G.
Ah, got it.
Good, very good question. I haven't said that. And we have a generic shape of all cycles that could happen. And that generic shape is that we have L blocks. And on each block of size 2, basically have the roots of unity. The first block is the roots of unity that we pass at speed 1. And the S block, we pass the roots of unity at speed n. And that's it. That's our most advanced result that I wanted to bring you to. This is valid, from my understanding, for almost any first order method that you would look at. If you want to find, all I've done is purely generic. We have done it on a heavy ball, but we can apply that to almost any situation. The symmetrization, the circulation, and the fact that if there exists a cycle for some parameters, then there exists a cycle that has that shape, that's purely systematic. And how now we're going to solve the heavy ball? I was telling you that we can find a short story. Actually, the one thing we're going to look at is only the first one. We're going to only look at roots of unity in dimension 2, and I could have just told you that. We look at that and not explained why we would look at that. That would have been an easy solution. But for me, most of the interest in the construction, that is underlying. So I have a circle on the roots of unity, if and only if, again, I have specific values for the gradient such that the momentum cancel to get that, okay? And now I can actually do a bit of math, which is just technical, and it says that it's not very difficult to find that it's actually a quadratically parameterized area that in terms of gamma and beta, that corresponds to the parameters for which I have a case roots of unity cycle. So now we really introduce something, a notation like that. If you ever look at the paper, which is a bit ugly, but which is the omega is the region over which I have a k. The circle is for roots of unity cycle. So that's the set of parameters for which I have a second roots of unity, third roots of unity, fourth roots of unity cycle, etc., etc. And now we have to put back things together. I have that area for which I have an analytical version. I have that plot, which is my rate on the quadratics, for which I know everything. And that's why I asked you to remember, I know that the sub-level sets are triangles. And we're going to look at the sub-level set with value, with rate 1 minus 50 divided by 3, let's say 17, 1 minus 17 kappa. So within that triangle, my rate is better than 1 minus 17 kappa, outside it's worse. And what I'm going to say is that basically that triangle in which the rate is at least 1 minus 17 kappa, not square root kappa, 1 minus 17 kappa, so no acceleration, is actually within the points over which I have a cycle. And so the points over which I have no cycle is extremely flat. And this is actually true for any kappa. Obviously, we have to verify for kappa small up to kappa very large that this phenomenon happens. And so the conclusion is the following one: for any kappa, for any set of parameters gamma and beta, either I have a function f in f nu L and an initialization over which I cycle, meaning that I'm in that triangle and thus within the purple region, so I have a function over which I'm never going to converge, or I'm not in the triangle, so I'm in the opposite region, I'm in the region in which I do not have a cycle function, but then my rate is at best 1 minus 17 kappa. So finally, what we say is that either there's a function that fails on smooth transforming convex, or there's a function, or the rate on the quadratics is not accelerated. That's really how it works.
But the cycle need not be attractive though, right?
The cycle need not be attractive for sure.
So it may be that you may have a cycle, but
Yes.
it converges for most points.
Yes, absolutely. Again, that's why I insisted on that's very, I think, hopefully it's on my conclusion side. Again, it's worst case analysis. It doesn't say that's what we have when we talk about the best convergence rate that we can get. We're saying there's no worst case convergence guarantee that is uniformly valid. That doesn't say that, I mean, and in any case, I could always consider all the functions that are all the functions that are quadratic within the class. On those functions, I'm going to converge. And same on some initialization, I'm going to converge. And if I show you the counterexample functions, and something even I should say that is very important. Actually, it is known that heavy ball accelerates on smooth and spherical convex functions if you converge. So this is also why I like the literature is extremely messy, because if you would converge towards the optimal point, then asymptotically you would accelerate. So when we have got that paper outside the head of my lab, it's called Grégoire, he's doing mostly analysis, and he came and told me I have the proof of the opposite in my lecture. Maybe we should talk. And we talked, and I convinced him that he assumes that he's in the neighborhood of the optimal solution. And if you're in the neighborhood of the optimal solution, you're locally quadratic, etc., etc. So if you initialize close enough, you are going to accelerate. And how much time am I going to time? Because I mean, we are done. Basically, I have extensions.
Can I have just one quick question? What is the white space that you have in between?
The white space, this one?
Yeah. What happens there?
Okay, so again,
I mean, you may have said something.
no, that's okay. Oops. Here, what we have is oops. Okay, let me on that plot is possibly a bit clearer. The purple area is the region in which we have cycles. So in all those we have cycles, and then on the next slide, I'm just now removing the purple to highlight the triangle in which my convergence rate is at least 1 minus 17 kappa. So basically the goal is to show that this is included into that. So in that area, I'm at least, only in that area do I have rate at least 1 minus 17 kappa, and only in that area do I converge uniformly for any function within the class F. So how am I going to time? I'm going 5 minutes. Okay, so very briefly, I can mention a couple of, yeah, sure, no worries.
I need to run.
No, of course. Just for fun, a couple of other problems. Stability against noise is actually something that's an extension. Basically, the way we build a function makes it possible to know exactly the shape of the worst case function. And we can ensure that basically there is some kind of distance between, so basically it's quadratic by parts. And I can force, if my perturbations are small enough, I can ensure that my perturbations always remain in an area in which I am locally quadratic, but with constant hashing, which says that if I force that, if my perturbations remain small enough, the system that my perturbations are going to face is exactly a heavy ball on a quadratic function. So the first stuff is small perturbations are going to be linearly passed through the system, and the system they pass through is exactly a quadratic system with identity hashing, and on that, heavy ball does converge. So, my perturbations are going to be attenuated. So my cycle is going to be somehow attractive with respect to minor perturbations. This is also how we can build actually afterwards, let's say a logistic risk that approximates that. We're going to use the fact that in some sense, some kind of universal approximation theory, I can approximate any smooth and spherical function by a logistic risk. And if I ensure that the gradients, function values are close enough to the function values and gradients that I need here, I'm going to have that particular cycle, say on the actual machine learning problem like logistic regression. Okay, so then we have questions on whether we can find an in-between class. The quick answer is that we cannot find something that by just assuming that the Hessian is Lipschitz. Again, there are at least 2 papers that claim the opposite. It unfortunately is not correct. And questions that are open. We released a small open we released a small open problems paper because we couldn't scrap a couple of things. We still don't know what happens in dimension 1 because the crux of our argument is those roots of unity in dimension 2. For that, in dimension 2 at least. In dimension 1, numerically, we have the same areas, but we don't know exactly. And there is a small region in which we don't know what happens. Here is the cycle, here there's a Lyapunov, and in between here, there is a question. So we scratched our heads a lot and then dropped it. So this is the conclusion. Thanks for your time. This is a bit of a journey. I'm happy to take any questions.